Hello friends, I am Dr. Jagdish Chand Bansal, Assistant Professor in the Department of Mathematics, Faculty of Mathematics and Computer Science, South Asian University. Today I am going to speak on some prerequisites to understand the word optimization. This prerequisite consists some basic definitions and the definitions related to the convex function and the convex sets. The very first definition is the convex combination. If x and y are two members in the Euclidean space Rn in the real space and lambda is a real number lying between 0 and 1, then the combination Z, which is lambda x plus 1 minus lambda y, is said to be a convex combination of x and y. This convex combination is said to be the strict convex combination if this lambda is strictly less than between 0 and 1, that is lambda is neither equal to 0 nor equal to 1, then this particular convex combination is known as the strict convex combination of x and y. The another definition is the hyperplane. A hyperplane in the Euclidean space Rn is the set of points x, which is again an n-tuple x1, x2 up to xn. If this set of points x satisfies the linear equation c1 x1 plus c2 x2 plus cn xn equal to alpha, where alpha is a fixed constant and c1, c2, cn are also constants, then this particular set of points is known as the hyperplane. A hyperplane is always a closed convex set, a convex set which is closed. The next definition is based on this definition of the convex combination. The definition is convex set. For your convenience, I mentioned here definition of convex combination Z equal to lambda x plus 1 minus lambda y. Lambda lies between 0 and 1. A convex set S is a subset of Rn, the Euclidean space, is said to be a convex set if it contains all convex combinations of pairs x and y belongs to S. There are two sets mentioned here. The first set is convex while the second set is not a convex set, because the first set, if you take any 2 points in this first set, within first set, then the line joining these two segment joining these 2 points will also lies within this convex set. But if you take 2 points in this second set which is non-convex, then the line segment joining these 2 points may lie outside the set, and therefore this set is known as a non-convex set. So a convex set, in another word, set can be defined as a set is said to be a convex set if the line segment joining any 2 points of this set also lies in the set, then the set is said to be a convex set. Some facts about convex set, that the intersection of any number of convex sets is again a convex set. Here are 3 sets, then the intersection part, this intersection part is known as a convex set. The next definition is the convex hull. The convex hull for a set of points x is the minimal convex set containing all points of x. This is the minimum set which contains x. Based on the definition of convex set and the convex hull, we can easily define the simplex. A simplex or n simplex is a convex hull of a set of n plus 1 vertices. A simplex is an n-dimensional analogous of a triangle, that is, a simplex is actually a generalization of a concept of the triangle in n-dimensional case. For example, if one simplex is actually a line segment, a 2 simplex is actually a triangle, and 3 simplex is a tetrahedron, and similarly a 4 simplex is a pentatop, and so on. Convex function is another concept, very important concept in the field of optimization. To understand the different kind of optimization problems, we need to understand whether the objective function is a convex function or not. So the convex functions definition is another important definition in this field. Let us consider S as a subset of Rn, the Euclidean space, a convex set. Then a function S whose domain is S and the codomain is the set of real numbers, a one-dimensional real space. Then this particular function C from S to R is said to be a convex function if C of lambda x plus 1 minus lambda y is less than or equal to lambda C of x plus 1 minus lambda C of y, where lambda, as in the definition of the convex set, lies between 0 and 1. Graphically, we can understand the concept of convex function. Suppose this function is the diagram for C, this is the graph of C, then suppose x and y are 2 points on the x axis and the corresponding function values are Cx and Cy as mentioned in this figure. This is the line segment joining these 2 points xCx and yCy. Now to understand the concept of this convex function through this graph, let us consider a point lambda x plus 1 minus lambda y between x and y on the x axis. This is a point between lambda between x and y. Here it should be noted that lambda must be lies between 0 and 1, otherwise this point lambda x plus 1 minus lambda y will go beyond the range xy, will either be less than x or will either be greater than y, and therefore to keep lambda x plus 1 minus lambda y within this range xy, you need to keep lambda between 0 and 1. The corresponding function value related to this C lambda x plus 1 minus lambda y is C of lambda x plus 1 minus lambda y. Then you can see from this figure all function values of this C are below the line segment joining Cx and Cy, and it is also clear from this definition of convex function that this C, the function value at this point should be less than or equal to, and therefore from this figure you can see that the function value of the function lies between x and y is less than or equal to this line segment, any point on this line segment, and this is the definition of the convex function. A concept about this convex function is that every linear function is a convex function. Actually there is another definition related to the convex function, that is the concave function, and I am going to mention that the definition in the next slide, but to mention it is worth to mention here that a linear function is also a concave function. So linear function is always a concave function and a convex both. These are some examples of convex functions: exponential x, minus log x, x log x. If you draw them and check the conditions of convex functions on these functions, you will find that these are the convex functions. Simultaneously, log of e to the power x1 plus e to the power xn is also a convex function. Another property of this convex set and the convex function is that feasible set of a convex optimization problem is convex. Actually in the next lecture I am going to describe the convex optimization problem, where you have a search space. The search space of the convex optimization problem, which is a feasible set, must be a convex set. Then only we say that this is a convex optimization problem. Next important definition is the definition of epigraph. Epigraph is the set consists of the tuple, two tuples xt, where x belongs to the domain of f, and corresponding value of f, that is fx, should be less than or equal to t. This is clear from this figure that corresponding for all values of x, corresponding value of fx is always less than or equal to this top value on the top line. This particular top line is known as the t, this point is t. So this all function values are less than or equal to t. Related to epigraph, a function is convex if and only if its epigraph is a convex set. Very important result related to the convex set, that this gives you a necessary and sufficient condition for deciding that a particular set is a convex set or not. So if this condition is satisfied, that its epigraph is a convex set, then the corresponding function will be the convex function. The last definition corresponding to the prerequisites of optimization is the concave function. We have already defined the definition of convex set. Set S in the Euclidean space Rn is a convex set, and suppose C is a concave function from S to R. You need to note it that this R is actually a one-dimensional real space. This function maps n-dimensional to the one-dimensional. Then this particular function, convex function C, is said to be a concave function if this minus C is convex function. Means if minus C is a convex function, then the corresponding C will be a concave function. Similarly, if C is a convex function, then minus C will be a concave function. These are some prerequisites to understand the concept of optimization. Based on these definitions, we can define the word optimization and some standard problems related to the optimization. Thank you very much.